In the previous lecture, for an oriented vector bundle pi from E to M, we defined the integration along fibers map from and let us begin by checking that this induces a map of complexes. Pi lower star commutes with the differential D. So proof. Let U alpha be a covering of M by coordinate open sets over which E is trivial. Let rho alpha be a partition of unity subordinate to U alpha and let rho alpha tilde be rho alpha composed by then omega, uniform omega can be written as pi rho alpha tilde omega. So since both pi lower star and D are linear, it suffices to check that they commute on rho alpha tilde times omega, which is supported inside pi inverse U alpha over which we have global coordinates. So thus we may assume M is equal to Rn and Rm and E is equal to Rm cross Rn. So as before, we need to consider two cases. So first, assume omega is equal to f of x t dxi wedge dt1 dtn then d omega is equal to summation over j naught in I tf by txj txj wedge dxi thus pi lower star d omega is equal to summation j naught in I integral over the fibers df by dxj dt1 and it is clear that this is equal to d of pi lower star omega. Since we can differentiate under the integral. Next, let us consider the case that A be a subset of 1 up to n, P of cardinality n minus 1, and assume A naught does not belong to A. So let omega be equal to f xt dxi wedge dta. Then d omega is equal to summation j naught I df by dxj dxj wedge dxi wedge dta plus df by dx a naught dt a naught. dt a naught wedge dxi wedge d d sub. So pi lower star of omega is 0 by definition. So let's consider pi lower star d omega. That is equal to minus 1 to the power cardinality of I plus a naught minus 1 integral f df by dt a naught d d1 ddn dxi. And this is equal to 0 since f is compactly supported along the fibers. So we could have This integral is equal to this one. So where we skip dta not here. This is 0. So if cardinality of A on the other hand is strictly less than n minus 1, then both pi lower star, let's just write this down. If cardinality of A is strictly less than n minus 1, then pi lower star W and pi lower star TW are 0. So this completes the proof of the proposition. As a corollary, we have maps which we continue to denote pi lower star. Sorry, H star minus n, where n is the rank of E. So let us now prove a formula which is called the projection formula. So pi lower star of pi upper star tau wedge omega is equal to tau wedge pi lower star omega, where tau belongs to H star m and omega belongs to H star vertical E. So proof again by taking the partition of unity we may assume that M is Rm and E is a trivial bundle. Let tau be equal to g of x dxj and omega be equal to f of x d dxi h dt1 h ddn. If dt1 up through ddn is not a factor of omega, then clearly, let me just write this down. Is not a factor of omega, then it is not. And so both so in this case the equality is trivially true. So let's consider the case where it is a factor. So then we have pi upper star tau wedge omega is equal to g of g of x dxj which dx. So now it is trivial. To check that proposition. So suppose M is an oriented manifold and tau is a compactly supported M plus N minus R form on M, and omega is a compact vertically supported R form on E. Then the integral over E. Okay, so let E be an oriented vector bundle. So by earlier lemma, E is an oriented manifold then the integral over E pi upper star tau wedge omega is equal to the integral over M tau wedge pi lower star omega. So in the above we give E the orientation dx1 wedge dxm wedge dt1 wedge dtn, where dx1 through dxm is the orientation on M, and dt1 through dtn is the orientation chosen is the orientation chosen on the fibers of E. So as before, using a partition of unity, we may assume is Rn and E is Rn, close Rn. Then pi upper star tau. So once again, so let tau be g of x dx j and omega be fx t dxi wedge dt1 to dtn. Then pi upper star tau wedge omega is equal to g of x f of x t dxj dx I wedge dt1 wedge ddn. So this is equal to -1. So if I intersection j is non-empty, then this is 0. Otherwise it is -1 to the s g of x f of x t dx1 wedge dxm wedge dt1 wedge ddn, and then integral pi upper star tau wedge omega is equal to -1 to the s integral m cross Rn on the other hand. Tau wedge pi lower star omega is equal to g of x dxj wedge integral over the fibers dxi. So once again, if I intersection j is non-empty, then this is 0. Otherwise there is -1 to the s into integral g of x f of xt dt1 ddn into dx1 wedge dxm, and then this implies integral over m tau wedge pi lower star omega is -1 to the s integral over the base, then integral over the fibers dxm, but this is equal to let's put this R in. So this completes the proof of the proposition. Now let us prove the Thom isomorphism theorem. Let E be an oriented vector bundle. over a manifold. M of finite type. Then pi lower star is an isomorphism. So proof let us first show that this is true for the trivial bundle. M cross Rn. So by induction on N, it suffices to prove this. When N is equal to 1. So yeah. So this is because the maps, so suppose we have, for instance, let's take M cross R2 to M cross R to M. So let's consider these maps M, X, Y, M, comma X. So let's call this pi 1 and let's call this pi 2. So pi 2 composed pi 1 lower star is equal to pi 1 lower star pi 2 lower star composed pi 1 lower star. So therefore this implies that suffices to prove pi lower star is an isomorphism when N is equal to 1. So let us prove that. So in this case, we have defined a map of complexes pi lower star from so we can define a map of complexes E lower star. So E lower star goes from as follows. This is something which we have seen earlier also. Choose an EFT such that integral is 1, such that EFT is compactly supported. It is compactly supported. And integral EFT dt is equal to 1. So define kilo star of omega to be equal to omega wedge EFT dt. Then clearly E lower star composed by lower star is equal to identity. Now it's the other way around. First I apply pi lower star compose E lower star is equal to identity. We need to check that the map on cohomology induced by E lower star composed by lower star is the identity. For this, it suffices to show that E lower star composed by lower star is homotopic to the identity. Of complexes. The homotopy operator is defined exactly as in the proof of the isomorphism and the rest of the proof proceeds in exactly the same way. Thus, we have proved that pi lower star from H compact vertical M cross R to H star minus 1 M is an isomorphism. So, which implies pi lower star from H M cross Rn to H star minus N is an isomorphism. So now we are ready to prove Thom's theorem. Let's consider the base case for the induction. So the proof is going to be by induction on the finite good cover of the base. So let M be Rm. Then since Rm deformation retracts, to a point, we get that if V bundle is trivial, thus from what we saw above, from what we just saw, we get pi log star Rm cross Rn to H star minus N Rm is an isomorphism. Now consider the more general case. Let M equal to U union V, and let rho U, rho V be a partition of unity. Subordinate to U and V. Then we have a short exact sequence. So we denote by tilde excuse me, is pi inverse U. Gamma compact vertical E So the arrow on the right is given by alpha comma beta, gets mapped to alpha restricted to U intersection V tilde minus U intersection V tilde. So the sequence is also exact on the right, since omega in compact vertical U intersection V tilde exterior, let's say R, can be lifted to rho V tilde omega minus rho U tilde omega, where rho V tilde is equal to rho V composed by and rho U tilde is equal to rho U composed by. Thus, we get long exact sequences and maps HR all the vertical arrows are pilo star. We need to check that the squares commute. This is an argument we have seen several times, and the only non-trivial check is with a square which contains the connecting homomorphism. It's the commutativity of let's call this delta tilde. Let's call this delta. Recall the definition of the connecting homomorphisms. Delta tilde and delta. So let omega be in V comma P such that d omega is 0, then there is a unique omega prime in e comma r plus 1 omega such that omega prime restricted to u tilde is equal to d rho v tilde omega, and omega prime restricted to v tilde is equal to minus d of rho u tilde omega. And then delta tilde of omega is defined to be this unique omega prime. Clearly, pi lower star omega prime restricted to u is equal to pi lower star of omega prime restricted to u tilde. This is equal to pi lower star of d rho v tilde omega. This is equal to d of pi lower star of rho v tilde omega, but this is equal to d of rho v of pi lower star of omega. So all this is happening on u, so that's fine. Similarly, pi lower star of omega prime restricted to v is equal to d minus d of rho u pi lower star of omega. So this implies, by the defining property, of delta, that delta of pi lower star of omega prime is equal to delta of pi lower star omega. Now by induction, on the cardinality of the finite good cover, we can complete the proof of the theorem. So in view of the above isomorphism, so in view of the above isomorphism, pi lower star let phi of e inside Hn be the unique element such that pi lower star of phi of e is equal to 1. this element is called the thumb class. Thumb class of E. So what this means is that this means that the zero form pi lower star phi of E on M is the constant function one. Equivalently, closed form phi satisfies pi lower star phi equal to 1 if and only if when we restrict it to any fiber which is compactly supported n form on Rn has integral 1 for all x in M. So as a consequence, we see that if we have a diagram like this, so E to M is a smooth bundle and M prime to M I have a map F, a smooth map. Then we get F tilde upper star and F tilde upper star of phi of E is equal to phi of F upper star E. This is clear. Since for all M prime in M prime we have F tilde upper star phi of E when we restrict it to pi inverse x is equal to 1. So this is a local check. And we immediately reduce to the case. And then the assertion is obvious. So the assertion is that the Thom class of f upper star E is the pullback of the Thom class of E, and this is checked by checking that the pullback of the Thom class of E, when we integrate it on any fiber m prime in any fiber over m prime in m prime, well, small m prime in capital M prime, the integral will be 1. So this is a criterion which we will use later. And let's just see one application of this criterion before we end the lecture. Suppose E and F are oriented vector bundles. On M, consider the bundle E directs some F with projections let's call this P1 and let's call this P2. Then we claim that the Thom class of E directs some F. This belongs to R plus S. So R is the rank of E and S is the rank of F. E directs some F. This Thom class, this thing is equal to P1 upper star phi of E wedge P2 upper star phi of F. Once again, this is clear because P1 upper star phi of E wedge P2 upper star phi of F has compact vertical support. And has integral 1 on the fibers. So we will stop here.